In this video, we'll do an example in which we find the domain of a function that has a square root restriction. So I want to find the domain of g of x, which is the square root of x squared minus 4 over x squared minus 2x, and to write our answer in interval notation. So I want to begin by thinking about the restrictions on the inputs. So the restrictions on the numbers that we can plug in for x. And in this problem, there are two domain restrictions. One of the restrictions is that there's a denominator. So the denominator x squared minus 2x cannot be equal to 0. And we actually handled this restriction in the previous video, where we had essentially the same function without the square root. And we figured out the only values that made the denominator be 0 were 0 and 2. So from this restriction, it's telling us that x cannot be 0 or 2. The other restriction is the fact that we have this square root. And the stuff inside of the square root, which is x squared minus 4 over x squared minus 2x, the stuff inside has to be greater than or equal to 0. That's the other restriction that's happening, because if the inside of the square root is negative, we are going to get an imaginary number, and we're not talking about imaginary numbers in our class. All of our functions need to have outputs that are real numbers. All right, so this, again, is coming from the fact that the inside of the square root needs to be greater than or equal to 0. All right, so at this point, let's do a brief review on how we solve inequalities. So review, because this one ends up being a little bit trickier than we might think initially. So first, how do we solve what are called linear inequalities? So linear inequalities. So let me give an example. So linear means it's going to sort of resemble the equation of a line, something like mx plus b. And then there's going to be some inequality symbol. Let's just say it's a greater than or equal to, like we have, but it could be any inequality symbol. And let's just put 0 on the other side. But it could be technically any constant here. So as an example, let's say we had negative 2x minus 5 is greater than or equal to 0. And to solve these, we just isolate the x. So if I add 5 over, we get negative 2x is greater than or equal to 5. And then I can divide by negative 2. But if I divide an inequality by a negative number, then I have to flip the inequality symbol. So I'll get less than or equal to negative 5 halves. Okay, so our strategy here with a linear inequality was isolate the x. But it turns out that this technique of isolating the x doesn't work. This doesn't work for nonlinear inequalities. For nonlinear inequalities. So let's quickly look at why. Why would this not work for our problem? So e.g., we have x squared minus 4 over x squared minus 2x is greater than or equal to 0. So let's say we were going to try to isolate, and maybe seeing this fraction, we think, let's multiply both sides by the denominator, x squared minus 2x, multiply both sides by the denominator, because that's a really common thing that we do with equations. And if we do that on the left-hand side, we're left with x squared minus 4. On the right-hand side, we'll be left with 0. 0 times anything is 0. And now there's the matter of, well, what happens to the inequality symbol? Does it stay the same? Or does it get flipped because maybe I'm multiplying by a negative number? So the thing is, with x squared minus 2x, this could be positive for certain values of x, or it could be negative for certain other values of x. So it's unclear whether to flip the inequality or not. So one of the ways that we could do this is consider the different cases, like when is x positive and when is x negative. and do the inequality individually for each of those cases, but it would be nice if there was a more efficient way, and that's what I want to show you. All right, so to solve a nonlinear inequality like what we have, we're going to use a method called the cut point method. Okay, and I'm going to highlight this. So the cut point method. Okay, so I'm going to break this down into steps. The first step is move all the terms to one side in our inequality so that the other side is 0. And if we look at our inequality, it's x squared minus 4 over x squared minus 2x is greater than or equal to 0, which means all the terms are already on one side. The other side is already 0, which means this step is already done. So that's kind of nice. Step 2 is to find what I'm going to call the cut points. So these cut points are values that make our expression, this x squared minus 4 over x squared minus 2x, our expression either equals 0, or I'll write equals 0 like this, equals 0, or that make the expression undefined. Okay, so let's find both of those. So if I want to make the whole thing equal 0, let's just set the whole thing equal to 0. X squared minus 4 over x squared minus 2x equals 0. And now that this is an equation, now I can do things like multiply both sides by the denominator just fine. So multiply both sides by x squared minus 2x. And when we do that, we're left with x squared minus 4 on the left and 0 on the right. This I could factor. This is a difference of squares, as x minus 2 times x plus 2 equals 0. And now I see that x equals 2 or negative 2. But there's one thing I have to be super careful about, which is, remember that when we talked about extraneous solutions, one of the situations where I have to check for extraneous solutions is if we have variables in the denominator. So that was this fourth case here. Check for extraneous if we have variables in the denominator. And we could even do this in our heads, but if you take 2 and you plug it into the denominator, you're going to get 0. That means 2 is actually extraneous, so we have to be careful. Negative 2 is just fine. If you plug that into the denominator, it doesn't make it 0. Alrighty, so when is this whole expression equal to 0? Well, it happens when x is negative 2. Now let's figure out when our expression is undefined. So it's going to be undefined when the denominator is 0. Undefined when x squared minus 2x equals 0. So let's factor this. We get x times x minus 2 equals 0. And I get x is either 0 or 2. Those are the values that make my expression undefined. All right, so we can now write our cut points. So we have these equal 0 cut points, which were just negative 2. And then we have the undefined cut points, which were 0 as well as 2. Alrighty, so that is step 2 of the process. Step 3 says, plot the cut points on a number line, and then make a sign chart of our expression. So we want to know when our expression is positive and when it is negative. So our expression was here, x squared minus 4 over x squared minus 2x. I'm going to use the factored form of this. So the factored form is x minus 2 times x plus 2 on the top. That was the difference of squares. And the bottom was x times x minus 2. And now I'm going to form a number line and plot the cut points on it. Negative 2, 0, and 2. And now what I'm going to do is, in my expression, every single factor that shows up on the top or the bottom, I'm going to write a row for it. So for example, I see x minus 2 on the top. I also see x plus 2 on the top, x on the bottom, and x minus 2 on the bottom. Each one of them gets a row. And now I'm going to separate out into columns where each cup point is, and then draw horizontal lines to form these rows. And in each one of these sections, I want to figure out, is this factor positive or negative? So for example, if I had a number smaller than -2, like maybe -5 is somewhere in this interval, and I were to plug that in to x minus 2, I'd get -7. So I get a negative value here. What about if I plugged in something between -2 and 0, like -1? If I plug that into x minus 2, I still get a negative value. If I keep going like this, if I plug in something between 0 and 2, like 1 into x minus 2, I still get a negative. But when I plug in something bigger than 2, like 3, this becomes positive. So I'm going to do sign analysis in this way. A quicker way that I could have recognized that it went like negative, 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 positive is to think about, when does x minus 2 change sign? I know that x minus 2 is going to be 0 when I plug in 2. And when I plug in things that are bigger than 2, it's going to be positive. And that's why it was positive over here. And when I plug in things smaller than 2, x minus 2 is going to be negative. And that's a quicker way to recognize that. So let's use that idea for the next factor. X plus 2, when does that change sign? Well, it equals 0 when we plug in -2. And when I plug in something smaller than -2, this is going to be negative. When I plug in something bigger than -2, in all those situations, it'll be positive. All right, so when does x change sign? At 0. When I plug in something bigger than 0, it's going to be positive. And if I plug in something smaller than 0, it is going to be negative. X minus 2, we actually did this one already. It was at the top. It's just repeated. So I know that this is negative, 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 and then followed by a positive. Okay, so I now need to write the sign of this whole thing. So I need to multiply the signs of each of these factors. So if I had a negative times a negative times a negative times a negative, 4 negatives, that makes a positive. The next column has 3 negatives and a positive. That multiplies to give me a negative. The next column has 2 negatives. That will multiply to give me a positive. And the last column has all 4 positives, so that will be a positive. All right, so I'm getting closer. Now I know when my expression is positive. So we are on to the last step. The last step will tell me, well, what parts of the number line do I actually shade so I can get my domain? So we're going to shade intervals where the inequality holds. So we care about when our fraction is greater than or equal to 0. So we are going to shade in sections where this whole expression is positive. But I need to know, how do I handle like open circles and closed circles? So undefined cut points. And what was the undefined one? Those were 0 and 2. The undefined cut points will always have open circles. Because if you try to plug in one of these undefined cut points like 0 or 2 into the inequality, it's going to make our expression undefined, and that just makes the inequality false right off the bat. So 0 and 2, those were the undefined cut points. They're going to have open circles. For the equals 0 cut points, that was the -2. Remember, -2, x equals -2, that was what I got when I set my whole expression equal to 0. Those are sometimes open and sometimes closed. So those equal 0 cut points have closed circles. They have closed circles if the inequality has equal signs. So what I mean by that is if it's either greater than or equal to or less than or equal to. It needs those equal signs. So the reason why that is, if it has an equal sign and I plug in one of these numbers like -2, remember that plugging that in was making my expression 0. And the other side of the inequality was 0 because we moved everything over to make it 0. And then if I have a symbol like this, like a greater than or equal to, this is true. This is going to be true because we have that equal sign there. And that's going to happen with our inequality because our inequality had this equal sign. All right, so I'm going to put a closed circle there. But let's quickly talk about, well, what would happen if our inequality doesn't have an equal sign? So we would put open circles at these equals 0 cut points. Otherwise, so that's if I have a less than symbol or a greater than symbol. The reason why is if our inequality was like that, and I plugged one of these equals 0 cut points in, I'd have 0 on both sides, but now I have something like 0 is greater than 0, no equal sign, and that's false. Okay, so now I know how to put open and closed circles. Remember, I cared about when this whole thing was greater than or equal to 0. So I'm going to shade in the regions where it's positive. So I got to shade in this region where it's positive, and this region where it's positive, as well as this region. And now let's write that in interval notation. So let's zoom it out a little bit. Okay, so our domain, I'll just write D for domain, is negative infinity to negative 2 bracket, union 0 to 2 in parentheses, because they're not included, union 2 to infinity. Okay, and I'm running out of room here a little bit, so I'm going to move that to the next page. So here is our answer at the top. So I want to end with a question, which is, why does this cut point method work? So to answer this, I want to look at an example of a graph so we can see that visually what's going on. So I'm going to call this function that I'm about to draw y equals f of x, but it's just going to be some arbitrary graph. And the graph is going to start down here, it's going to go up, and let's say it crosses the x-axis at -5. So at -5 here, and then it's going to curve downwards, and then it's going to touch back at 1. It's going to have a hole there, and then it's going to keep going downwards. Let's draw this better. It's going to keep going downwards with an asymptote here. So it goes downwards, and let's say the asymptote happens to be at 6. And then on the other side of the asymptote, the function looks like that. So asymptote's up this way, and then going in this direction, it just goes up and up and up. Let me put an arrow here so that it continues on downwards that way. So what we want to be able to do with this cut point method is we want to find, the general question is we want to find where our function f is positive and where f is negative. That's our question. And to answer this, we need to find where it switches sign. If we can figure out the values where my function switches sign from positive to negative or negative to positive, we have a really good insight into answering this question. So if I look at the graph and think about, when does my function switch sign? When do the outputs or the y values change from negative to positive or positive to negative? One of the places it happens is here, where it actually touches the x-axis. So this is where my function equals 0. So this is one of those equals 0 cut points. And that's not a coincidence. And the other places where it switches sign is at this hole. That's not an equal 0 cut point because it's not actually defined there. Otherwise, it would have been a closed circle. And it switched signs at this asymptote. So these places are where the function was undefined. These are undefined cut points. Undefined cut points. So if I want to find where it switches signs, we now notice that this only happens at the cut points. And that is the key right there. When we do the cut point method, we are first figuring out, well, where are those cut points? And then when we do the sign analysis, like we did in this sign chart, so once we knew where these cut points were, then that sign analysis helps us figure out, well, between the cut points, what is the sign of the graph? It's either going to be negative or it's going to be positive. So we are going to see sign analysis show up later in our class when we talk about derivatives. We're going to be interested in when are derivatives positive and when are they negative, because that has a special meaning. So finally, in terms of our goals, we finished our final goal for our review section. We've reviewed finding domain and solving nonlinear inequalities.